everyone, and thank you for coming. Today I'll be talking about, my name is Phillip Schönfelder, and I conducted a research topic with my supervisor, Markus König, which was the topic deep learning-based entity recognition in construction regulatory documents. And first of all, I would like to give you a short introduction about the research task of the rule extraction from regulatory documents. Since if you have a virtual building design, and you want to check it against certain rules that are imposed on the design, let's say from law text or national standards or even contract-specific requirements, then the rules have to be present in sort of a machine-readable format, so the computer can process them automatically and check the model against them. However, the rules originally come from documents that are fluently written text, and those are typically only human readable. So there has to be a transition. These rules have to be transformed from human readable to machine readable. And if this is carried out by a domain expert, it's quite the time-consuming task and also quite error-prone. So it is anticipated to automate this task of rule transformation. In order to do that, there exist a lot of natural language processing techniques. But in this study, we'll mostly deal with transformer models. Transformer models are state-of-the-art language models that have, in many applications, superseded recurrent neural networks, or RNNs. Not in all the applications, but in many of them. And that is mostly because they have the capability to be trained in parallel. So all the computations needed in order for them to be trained can be carried out in parallel. And that allows the training to be carried out much more efficiently. So, and that makes training on huge amounts of data even possible. So that results in very nicely trained, pre-trained models actually that come with a very high degree of language understanding. So the motivation for the study is to test one of these language models with the simple task of named entity recognition. That's a very basic task in text processing. Basically, it's to detect phrases and classify these phrases into predefined classes within a sentence. So the input to the model would be a sentence, and then the output would be a list of labels, and each of the labels would stand for one word in a sentence. And the question is, there already exist so many powerful English language models, but are there also German models, and that can be used for this task? And also, are they capable of dealing with domain-specific text, for example, from the construction domain? So in order to test this, we assembled a document corpus. So there are 16 federated states in Germany, and each of them has their own building code. So there are 16 building codes in total. However, due to time limitations, we only took 4 of these building codes and built a corpus from them. So the first thing we did is we converted them from PDF format to simple ASCII text files. And then the next thing is we ran a natural language processing pipeline to segment the documents into sentences. So this was carried out with the Spacey library. And then after that was done, we could simply remove all the sentences with a word count below 15. This is due to the fact that there are a lot of short sentences, if you want, like headlines or page enumerations or even hyperlinks or cross-references that are simply shorter than that, and they do not carry any semantic meaning whatsoever. So those were included, and then we were left with 2,500 sentences from the documents. And these were then manually annotated regarding a certain named entity scheme. And here are some of the classes from that scheme. So on the left side, I've highlighted some of the entities in the IFC scheme that could be directly matched to the classes. So for example, IFC actor, IFC building, IFC building story, IFC building element. And then there are also other entity types, for example, document type descriptions or geopolitical entities or references to other law texts and numerical values. The model architecture we use for this is based on a transformer model and also on a very specific and pre-trained transformer model called BERT. BERT is kind of the most famous transformer model out there. And there also exists a German version of the model that has the same architecture, but is trained on German corpus, for example, including the German Wikipedia. And what the model does is 2 things. The first thing is it tokenizes the input sentence into smaller parts. So typically tokenization would mean to split the sentence into single words but this one goes a step further. It even tokenizes it into sub-words. So those might be syllables or suffixes, prefixes, or even single letters, so that every possible word can be combined with these word pieces. And then afterwards, each of the word pieces is embedded into a vector of size 768. So that is quite a vector. And then after that, after the sentence is encoded into a series of vectors with that length, we added a dropout layer for some regularization to prevent overfitting. And then in the end, we added a dense layer simply for classification that would leave us with a probability score for each of the words to fit in a certain category. So visualized, there is a small example on the bottom. So the input sentence would be windows with a minimum parapet height of 0.9 meters are permitted in outer walls. And then the model would tell us that windows and outer walls are instances of building elements, and the 0.9 meters is a numerical value. That's the idea. In order to test the model's performance, we took the whole corpus and performed firstly, we performed a four-fold cross-validation. So this is a very basic experiment, and we thought it makes sense to make it four-fold since there are 4 documents in our corpus. So this helps us to train the model on as much data as possible while still having a good experiment routine. So, and the second experiment was to only train the model on one of the documents and then test on the remaining 3. Since we know that the annotation of the documents is time consuming, and we cannot be sure that domain experts might have the time to annotate as much data as the model might need in order to perform best. So the question is, how well does the model still perform if we only train with one of the documents? And here you can see a summary of the results from the experiments. So on the left side, there is a table containing all the performance scores of the first experiment, the cross-validation experiment. And on the left, in the left column, you can see the state codes. So these are simply the names of the states in Germany where the law text came from originally. And then for each of them, we have a precision and recall and F1 score if we test the model on that specific text. And really the most important score in the table is the F1 score, which for the cross-validation experiment is 95.4%, which is a decent performance. And in the other table on the right side, we see the results of the other experiment where we only trained on one text. And even there, the performance is only slightly lower. We have almost 93% F1 score there. And that tells us that even with very little training data, the model can perform quite well. And that is mostly due to the fact that it has been pre-trained on such a large corpus that it already comes with a sort of language understanding, and we only have to fine-tune it in regard to our domain-specific language and the specific task at hand. So let me draw some conclusions from that. So first of all, we successfully employed a deep learning transformer model for named entity recognition in construction text. And to our knowledge, this is the first approach in that direction, and also the first approach for German regulatory documents. And with that, we achieved satisfactory performance. I mean, the training data set is not as large. You could, of course, enlarge it to get better performance. But we saw that even if very little training data is provided, as it was especially the case in the second experiment, there can be a satisfactory performance. However, there are, of course, some limitations. For example, the training data might not be diverse enough. So as I said, all the texts originate from state building codes from Germany, and they are inherently quite similar to each other. I mean, they differ in style, in formulation, and of course, also semantically, but they are the same type of texts. So one might have to test the model's performance on other texts as well and see how well it generalizes. So that brings me to future works. The model should be trained and also tested on more and more diverse text. So for example, national standards could be a source of text since they are freely available, and there are a lot of them, and they might differ more than these national building codes. And then of course, the named entity recognition might only be one building block in the whole rule extraction process. So this can also be enlarged. The process can be bigger in the end. So for example, you could include the extraction of the relations between the named entities to the process, which could also be carried out with such a transformer model. Okay, so let me leave with a final remark. the use of these transformer models for all kinds of natural language processing tasks is becoming easier because there are so many pre-trained models available. And I just want to encourage researchers in the construction domain who are dealing with NLP tasks to make use of these transformer models and of the pre-trained language models. I'm sure there are models for French, Italian, Spanish, also Arabic and Chinese, or in Portuguese. So that there might be something for you and for your research. Okay, so that is it. I'm happy to answer your questions now. Thank you for your attention.
Thank you, Philip. So we already have one question from Amin Hamad. How is this work related to smart codes? Smart codes.
To smart codes?
Yeah.
Could you elaborate on that?